Okay, so in this circuit we have uh, three loops, one on the left here, one on the right here, and of course this outside loop we could write KVL for any of them. This method of using Kirchhoff's current law and Kirchhoff's voltage law generally expects us to write KVL around the two inner loops, and then Kirchhoff's current law at enough nodes to give us well, three equations. And so now, with respect to the polarity, you'll notice that the polarity of the 2-volt source is positive on the bottom, which means that the current probably comes out of the bottom of him and into the top. And so I've labeled I1 then from right to left in that branch. Likewise for the 4-volt source, then the current probably comes out of the top and goes up, so I've labeled I3 in that direction. For the 6-volt source, the current probably comes out of the top and goes from right to left, so I've labeled I2 in that direction. I've called the junction right here A. And you notice that the solution is given there already, but it's our job now to write equations to come up with that. Okay, so generally what we want to do then is for each loop start in a bottom right hand or left hand corner and go around the loop in the direction of assumed current and write a KVL expression or equation. And so this if we start here and we'll go around in the direction of assumed current, and so if we call this here loop 1, then we'll start by saying KVL for loop 1. And remember, now we're going in the direction of assumed current, so counterclockwise, and we go across the 4-volt source. That's a rise in potential, so plus 4. And if we're going to put polarity on our resistors, then if our direction of assumed current is this way and then this way, and for this one here, if I2 goes from right to left, positive on the right, negative on the left. So back to our loop equation for loop 1. If we're going across R3, we're going from a positive sign to a negative sign, which represents a drop in potential. So negative VR3. VR3 by Ohm's law, I times R is 560 multiplied by I3. And so then the next device is R1. And again, if we're going counterclockwise here, it's from a positive sign to a negative sign, so a drop in potential. Negative 1000 multiplied by I1. Now our 2-volt source, we're going from a negative to a positive, so that's a rise in potential. So we have plus 2. We have completed the loop. That sum is equal to 0. Now we should simplify basically as much as we can. And so if we're going to make the coefficient on the first variable in the first equation positive, we have then, we'll start off with 1000 I1, so then plus 560 I3 is equal to 6. And so the reality of it here is that even though I got these numbers on the left, I kind of moved them across the equal sign in comparison to the plus 6. Okay, and so now if we're going to solve this with substitution, these circuits laid out with two loops, one on either side of this center branch. They always works out to, this loop on the left over here does not have a term for I2. The loop on the right does not have a term for I1. And KCL got all three variables in it. And so generally what we want to do is solve, oh, and this was a 1 here, solve these equations for the two loops in terms of something is equal to expression with I3 in it. And so what I'm getting at is we can solve this right now for I1 in terms of I3, or we can do it later. And so let's go ahead now and do it before we write the next equation. So we have 1,000 times I1 is equal to 6 subtract 560 times I3. And so that means, I keep forgetting my subscript on the I1. I1 then is equal to 6 subtract 560 I3 divided by 1,000. And so what that means basically is that I1 is equal to 6 over 1,000 is 6 milliamps, right? And so we'll write it as 0.006 minus 560 divided by 1,000 will be 0.56. And so multiply that by I3, of course, and call that equation 1. Okay, so now we'll call this here loop 2, and our direction of assumed current for loop 2 is, again, we put I2 here from right to left, so again counterclockwise, and so we'll start here, and we write KVL then for loop 2. Okay, so again now, going around here counterclockwise. The first device is the 6-volt source. We're going from a negative to a positive, so that's a rise in potential, plus 6 across resistor R2 from a positive to a negative is a drop in potential, subtract 820 multiplied by I2. Now, when we come I3 here, we're going down, and it's from a negative to a positive. So the polarity is very important here. That's a rise in potential. So plus 560 times I3. Now, for the 4-volt source, again, from a positive to a negative is a drop in potential. So subtract 4. Now we've completed the loop, and so equals 0. Okay, so now for this one, we have 820 I2, subtract 560 I3. And so remember now, I changed the sign here on this term for I2, but you don't have to do that, right? I mean, everybody got their own method of doing algebra. And so once you got the KVL equation written, the simplification and the solution, is kind of a personal thing. And not everybody does that the same. So you don't exactly have to simplify my way. And so in any event, now I like to make this number here positive. And so 820 I2, subtract 560 I3. And on this left side of the equation, we have 6 minus 4, which gives us 2. And if I change the sign, that would be negative 2, but I brought it across the equal sign, so equals 2. Now, remember that this now becomes equation 2, but if I'm going to solve for something in terms of I3, then I want to say that, oh, wait, no, let me fix that. I want to say that I'm going to start off with my 820 I2. Is equal to 2 plus 560 times I3. So I2 is equal to 2 plus 560 times I3 divided by 820. And so that means that I2 is equal to 2 divided by 820. And so yes, you know, we're getting a decimal there, 0.00244, and you need to keep at least three significant digits there. Plus 560 divided by 820 is giving us 0.683, and of course that's multiplied by I3, and we'll call that equation 2. Okay, so now our next step is, remember, we want to write Kirchhoff's current law at node A, and that becomes our third equation. So let's do that. And so I'm going to put that over here just to keep it in view here. KCL at A. And we do that, remember, the sum of the currents that enter is equal to the sum of the currents that leave. And so, or, you know, the sum of all currents is equal to 0, with the notion that currents that enter are positive, currents that leave are negative, right? So either one of those works. And so you come up with the same result, right? So we got I2 plus I3 equals I1. Or, you know, we got negative I1 plus I2 plus I3 is equal to 0. I like to have this term as positive. It don't matter, right? These are all equivalent. I1 subtract I2 subtract I3 is equal to 0. And so, you know, if I multiply this whole equation by -1, I got this. And so either one of that works. And so we call that equation 3. Now remember that, you know, for substitution here, in order for us to come up with a value for I3, the easiest way to do this is to substitute equation 1 and equation 2 into, into equation 3. So now I've got to move down to do that. Okay, so we want to sub 1 and 2 into 3. And so when we do that, basically, we have I1, right? But I1 is equal to this expression. So we have 0.006 subtract 0.56 times I3 And then we have subtract I2. Subtract I2 is equal to this expression, 0.00244 plus 0.683 times I3, subtract I3 is equal to 0. Okay, now the next step then is for us to combine our like terms, and so we have now this term with I3, this term with I3, this term with I3, and so we have I3. Okay, just let me fix that a little bit there if I could. I3 then outside of negative 0.56. And so the negative sign says subtract 0.683, and of course the negative sign here means -1. Plus, I have now my constants to think about, 0.006, and the negative sign, subtract 0.00244 is equal to 0. Okay, so at that point I suppose I could have brought my constants here across the equal sign, but I'll do that now in a minute. So I3 is now outside of, I suppose, and I'm going to change that to, we'll put our coefficient for I3 in first now. And so we got this sum or difference, or whatever you like to say that. We got negative 0.56 subtract 0.683 subtract 1, and that's given us negative 2.243 times I3 plus we have a 0.006 subtract a 0.00244, and that gives us a positive 0.00356 is equal to 0. So if I move down a little bit, we have then, if we do this, remember that we're going to have now R3 is equal to 0.00356 divided by 2.243. And so these both got negative signs, or both got positive signs. The idea is that when we do the calculation, we're getting a positive value for I3. And if you work that out now, you come up with 0.00159 if we round it to 3 significant digits, which is 1.59 milliamps. And I think that that agrees with the solution that we had above. Obviously it does. And so now we have I3. Okay, so our job now is to find as well I1 and I2. And so from 1 and I'll go ahead now and do the calculations here kind of quickly. But remember that for 1 we had this expression here. So I1 is equal to 6 milliamps, subtract 0.56 times 1.59 milliamps, and so 6 milliamps subtract 0.89 milliamps. I rounded that to because we're going to have 3 significant figures after we do the subtraction, and so I1 is equal to 5.11 milliamps. Okay, and so the last thing now that we need is I2. So from expression 2, we have then I2 is equal to 2.44 milliamps, and you see me just writing that as a milli, moving my decimal 3 spots, right? Plus 0.683 times my I3, which was 1.59. I hardly got room there to squeeze in my milliamps. Okay, so now we have then I2 equals 2.44 milliamps plus 1.08 milliamps, and we add that up and we come up with I2 is equal to 3.52 milliamps. Milliamps. Okay, and so remember that right, if we're going to put this in the graphing calculator, and we may as well go ahead and show that now before we give it up. All right, and so the substitution for these networks that are laid out like that, they're all pretty much, they works out to that pattern. Okay, so your one loop equation solved for I1, the second loop equation solved for I2, substitute that into your Kirchhoff current law equation, come up with a value for I3, then go back to your 2 loop equations, come up with value for I1 and I2. And so, they all pretty much works out like that. Now, our matrix solution then, for this one, we go back to this expression for I1. And yeah, okay, so this expression right here is what we want to do, right? So we have 1,000. For I2 we have 0. For I3 we have 560. And so we would write down then our coefficients, 1,000, 0, and 560. For equation 2, it's this form right here that we're using. So we have 0, 820, and negative 560. So 0, 820, negative 560. And for our KCL expression, this one or this one, it don't matter which one, because they're both valid, and so they're giving us the same solution no matter which one of them we put in, right? Okay, so we have then we can use a 1 if we go with the bottom one, a -1 and a -1. And this is the coefficient matrix, and so it is the inverse of that matrix. And then we want to multiply that by the matrix of constants. And for the constants, we had 6, and we had 2, and we had 0. Okay, so we have here 6, 2, and 0. And if we put that into our calculator, we will come up with 5.11 milli, 3.52 milli, and 1.59 milli. And so of course they are currents because they represent I1, I2, and I3 respectively. And so, a bit faster to arrive at the matrix solution, no doubt about it. And our what we started out with was our solution right there. And of course, that matches our numerical result. Okay.